Hey everyone, welcome back to Linear Algebra. This is going to be lecture 14, and in this section we are going to continue with our discussion of vector spaces, and we're going to introduce the idea of a subspace. So let's go ahead and jump into it. And so we'll call this section 4.2 subspaces. Okay, so in our previous section we discussed the fact that, let's start with a motivating example. In our previous discussion, we talked about this example where we had P as the set of all possible polynomials. Okay, and specifically with real coefficients. Okay, we talked about this as a vector space. Okay, and then we also discussed the vector space P sub n. And so this was the vector space of all nth degree or less polynomials. This is the set of all possible nth degree or less polynomials with real coefficients. Okay. And so we saw that P of n was a vector space as well. Now the whole idea behind a subspace, it stems from the idea of when you have two vector spaces and one of them is a subset of the other. Okay, so this is kind of the motivating idea here, right? So you start with a vector space, and then you identify a subset of the vector space. In this case, we start with P, and we can obviously see that P sub n is a subset of P, and both of them are vector spaces. Okay, and so this is a great motivating example of the idea of a subspace. So let's go ahead and define it, and then bring this example back in on the other side of the definition. So we'll let V be a vector space. Okay, we'll let V be a vector space. Then W is a subspace of V if and only if W is a subset of V and W is itself a vector space. Okay, and we should say is itself a vector space with the same operations as V. Okay, so a vector space V, given that, W is a subspace of V if and only if W is a subset of V and W is itself a vector space with the same operations as V. So you can think of it like this. Right, if I've got my vector space V and inside there I've got some subset W. W is literally, if W is a subspace, then W is literally a vector space inside of another vector space. Okay, so if we let U and V be in W, which is a subset of V, right, then think about what happens when we perform the operation of vector addition and scalar multiplication on U and V. Then U plus V needs to be inside of W because W is a vector space. It's also a subspace, but it happens to be a vector space as well, so it's going to be closed. So elements inside of W will stay inside of W when you add them together or when you multiply them by a scalar. Okay, so if U and V are in W, then U plus V needs to be in W as well, right? And if A is some scalar and u is in W, then A times u needs to stay in W as well. Okay? And so subspaces are like subsets. Obviously, the objects of a subspace they'll represent a subset of some larger vector space. But in addition to just being a subset, you have to have this closure property. And right, so kind of a quick way to say that is W itself has to be a vector space, right? Which means you can't get outside of W using the normal operations of scalar multiplication and vector addition. Okay, perfect. Let's do an example. Actually, let's explore this polynomial example a little further. Okay, so P sub n is a subspace of P, right? So we already saw that P sub n is a vector space, right? But the thing here to notice with the subspace is that specifically, if you have two vectors in Pn, right, then u plus v is going to stay in Pn, right? And what that specifically means in the case of P of n is that u plus v the degree of u plus v does not increase. So the degree of u plus v is less than or equal to the degree of u or v, or the degree of v. Different ways to say this. That's one way to say it. Right? The degree here, well, a better way to say it would be it's less than or equal to the max of the degree of u, the degree of v. That's one way to say it. That's a better way to say it. Okay, so the degree of the sum is less than or equal to the maximum of the individual u and v degrees. All right, so let's do an example here. Let's flesh this out just a little further. Let's let Q1 and P, Q and P be in Pn. Right, so then what does that mean? Well, P is going to have the form of Pn x to the n plus ... plus P1x plus P0. And Q will have the form Qn x to the n plus ... plus Q1x plus Q0. Okay, and now notice, right, that when you add polynomials together, the degree does not increase. So P plus Q does not increase the degree. That's kind of the key to why this works as a vector space. That's why P sub n is a vector space, because the degree can't increase. Okay, right? So if I add these together, right, I just add the coefficients, right, and I still get the x to the n as the highest degree term, right? And so then I would have P1 plus Q1 times x plus P0 plus Q0, right? So this is still an nth degree polynomial. Now, while the degree cannot increase, it can decrease, right? So if I take, we saw this example last time, but let's just make sure that we see this. So P1, maybe I'll say that's x squared plus 2x, and P2 will make negative x squared plus 2x. When I add these together, what do I get? Well, I get x squared plus 2x plus negative x squared plus 2x. And so, of course, I get just 4x, right? So the degree can drop, it can decrease, but it can't increase, right? And so that's why we define P sub n as we do, right? Where we say P sub n is an nth degree or less polynomial with real coefficients. Okay. Right? So once you're inside of P sub n, two elements inside of P sub n can't get outside of P sub n. Right? So hence it's a subspace of all of the total space of polynomials of P, right? So P sub n is a subspace of P. Okay, I like that example. It's very concrete. It's something. These are familiar objects. Let's think about what is called the trivial subspace. Another example. If V is any vector space, so if V is any vector space, then V is a subspace of itself. Okay, so if V is any subspace, then it's a subspace of itself, right? Why would that be? Well, because V is a subset of itself, right? It's not a proper subset, but it is a subset. Right, so this is one of the trivial subspaces. Another one is the subspace zero, the zero vector alone. So if W is equal to the zero vector, right? We saw that was a vector space. Then W is a subspace of all V. Okay, so this is called the trivial subspace. Right, and they're called trivial. Why? Well, they're called trivial because every vector space has these two as a subspace, right? So every vector space, I guess what is implied here is that every vector space has at least two distinct subspaces. So every vector space V has at least two subspaces, and that would be V and the zero vector. Okay, excellent. All right. And so, the fact that V is a subspace of itself brings into question the concept of a proper subspace. So all subspaces of V other than V itself are called proper subspaces. Okay. All right. Perfect. Let's get a little out there for a moment. Consider the following chain of subspaces. Okay, consider the following chain of subspaces. Let's say we've got some P0, and we've got some P1, and we've got some P2. Okay, and somewhere down the line, we get the set, the subspace that consists of all differentiable real-valued functions on R. Okay, and I'm going to say these are all on R. Okay, real-valued functions on R. This itself would be a subspace of another set, which would be the continuous real-valued functions. Okay, on R, which would be a subspace of another set, which we could say is all real valued functions. On R. Okay. Right now, if you think about it, I mean, so these are all actually proper subspaces, right? These are all actually proper subspaces. So, right, they're all proper subspaces. And think about how that would be. I mean, we're not going to go through and rigorously demonstrate this, but think about how that could be the case, right? If you think about, take this one for example here. If you have two differentiable functions and you add them together, you get a differentiable function, right? A scalar times a differentiable function is a differentiable function, right? So there's going to be functions that are continuous but not differentiable, right? But any two functions in this set are going to be differentiable. Their sum will be differentiable, and a scalar multiple of them will be differentiable. So so once you are dealing with two items in here, and you're talking about vector addition and scalar multiplication, then you can't get above it, right? And so think about this set. When you have two continuous real valued functions, when you add them together, what do you get? You get another continuous real valued function, right? And there's no way to step out of the there's no way to get to a function that isn't continuous, starting with two continuous functions and just confining yourself to vector addition and scalar multiplication. Okay, so that's kind of a cool thing to think about. The context here, you know, if you think back to your calculus classes, a lot of the discussion was something needed to be continuous in order for it to be differentiable, but it was possible for some continuous functions to not be differentiable, and so on. So there's a whole chain of subspaces that are laid out that you could consider to be subspaces of all real valued functions. All right, let's take an example of where we have something that we might think of as a subspace, but not a subspace. So let's let W equal the set of vectors x, y such that x is greater than 0 and y is greater than 0. Okay. Now, we can clearly see, so clearly W is a subset of R2. Right? If you take the plane, it's obvious that W is a subset of the plane, namely it's the first quadrant, right? So this is the first quadrant. But is it a subspace? The plane, if you take all of R2 is a vector space. So R2 is a vector space. And W is a subset of R2, right? But is W a subspace? What do you think? Well, the answer is no, right? No, W is not a subspace of R2. How can we confirm this? Well, all we need is one example where an element in W two elements in W added together get you outside of W, or an element in W being multiplied by a real number get you outside of W. And we can easily find that. Let's let U equal 2, 2, which is obviously in W. Right? Now notice if I just take any negative scalar, so negative 10 times U, what is that? Well, that's negative 20, which is not in W. Okay, right. So that's enough to show that W, as defined, is not a subspace of R2. R2 is a vector space. W is a subset of a vector space, but it's not a subspace because it's not closed, in this case, under scalar multiplication. Okay, perfect. Excellent. So let's go ahead, and this kind of leads us to a nice theorem. Right, this is a nice theorem for identification of subspaces. We don't always want to have to go through and check all 10 properties of subspaces to confirm all 10 properties of a vector space to confirm that something's a subspace. We might be able to do it quicker, and indeed, this is the theorem for that purpose. Okay, so let's let V be a vector space. We'll let V be a vector space and let W be a non-empty subset of V using the same ops. As V, right? So, when we're talking about vector spaces and subspaces, there's some operations implied there, right? And so V is a vector space, W is a subset of V, then using the same operations as V. Then what we can say is W is a subspace of V if and only if W is closed. W is closed under the operations of V. Okay, namely vector addition, scalar multiplication. Okay. Okay, so what is this theorem basically saying? Well, it's saying if I have a vector space V and I've identified some subset of V. If I have a vector space V and I've identified a subset of V, then in order to confirm that W, my subset, is in fact a subspace, I need only show that W is closed. Okay. Okay, so let's prove this. This is a nice proof. Okay. It's an if and only if, so we're going to start with one direction, right? We're going to start by assuming W is a subspace of V. Right, this is the easy direction, right? So this just basically is where we need to, this is the easy direction, right? So if W is a subspace, that's what we start with, then W is closed, right? If a subspace is closed, naturally, right? That's the definition. If W is a subspace, then W is closed, and we can also say W is also a vector space. Okay, and so what do we get from that? We get all the properties of a vector space. Okay. Okay. Okay, well, so that's kind of that direction, right? Right. So if W is a subspace of V, then basically W gets all the properties of a vector space. Kind of done there. Okay. The other direction, let's go the other way now. This one is a little more involved. Let's assume W is closed under vector addition. And scalar multiplication. Okay, so we're going to assume that W is closed under vector addition and scalar multiplication. Then, given this, what do we need to show? What we need to show is that W is a subspace, so it's already closed under vector addition and scalar multiplication, but what we need to show is the other 8 properties hold as well. Okay, and so Many of these are straightforward. Right, so just kind of to make sure we're clear here. So we've assumed that W is closed under vector addition and scalar multiplication. Now, what we need to do to prove that it's a subspace is we need to prove that it's a vector space, right? It's closed, but do the other operations hold as well, the other 8? Closure was just 2 operations. There were 8 more, right? And so if we can show the other 8 properties hold, then this will imply that W is a vector space and hence a subspace. Right? And so what are the other properties? Well, I'm going to write some of them out here. Most of the other properties are true in W because they are true in V. Right, and then the idea here is that because V is a subspace, W is a subset of V, then W is going to inherit a lot of the vector space properties of V, right? And so specifically, we can go through a couple of these. U plus V equals V plus U. Well, we know that this is true because, first of all, the vector space properties of V mean that this is minimally in V, but then we also know that W is closed. All right, so if U and V start in W, because of the closure that we're assuming, U plus V has to remain in W, and V plus U has to remain in W. Okay, and so another one is U plus V plus W, the associative here. U plus V plus W. Okay, so that one works, right? Again, same thing. I mean, we inherit these from the vector space, V, right? V is a vector space. So property 5 we get for free. That's A times U plus V equals AU plus AV. Okay, we also get number 6 for free. That's A plus B times U equals AU plus BU. Okay, and we get 7 for free. And 7 says A times B times U is A times BU. Right, so again, another kind of associativity. And then we get this one, the scalar multiplication identity. So 1 times U equals U. Right, so we get all of these are obviously true because V is a vector space, and if these elements are in W, then they're naturally in V, and so all of these vector space properties hold. Okay, so these are true because W is a subset of V, a vector space. Okay, what about 3 and 4? What about 3 and 4? So let's talk about 3 and 4. We have to be a little bit more careful with these. So remember 3 says there exists the 0 vector in W such that 0 plus U equals U plus 0 equals U. Right, so basically we need this additive identity element 0 to be inside of W in order for it to be a vector space. Okay, that's 3. And so what we need to show is that if W is closed under vector addition and scalar multiplication, then this element must be in W. We'll have to prove that in a sec. We'll come back to this in a second. The other one that we don't get for free that we have to do a little work on is the additive identity, right? So we need to show that there exists a negative U in W such that U plus negative U equals negative U plus U, which is 0, right? And so just because U is in W, that doesn't necessarily mean that negative U is in W, right? We don't get that automatically. We have to show that that's true. So let's do these two. These are fun. So we'll start with 3. Well, so for 3, right, remember we're trying to show that the 0 vector is in W, right? So if W is non-empty, W is not equal to the empty set, then there's some vector w1 inside of w. Okay. Now remember, w is closed under scalar multiplication. Right? It's closed under scalar multiplication. So what does that mean? Well, it means 0, the scalar 0, times w1 needs to be in w. Okay. Okay. This is the same operation as in v, right? This is the same operation as in v. In v, 0 times w1 is just equal to the 0 vector, right? That's in v. Right. So what does this mean? Well, look, if w is closed under scalar multiplication and 0 is a valid scalar, then when I multiply 0 by any element in w, that implies that 0, the vector, must be in w. Okay, so we know that now. Okay, so the 0 vector is the additive identity here. It must be in w, right? And that's a consequence of the closure, right? W is closed. In order for w to be closed, that scalar multiple, multiplying by 0 has to be permitted, which implies that the 0 vector is there as well. Okay, now what about 4? Okay, for this one, so again, here we're trying to show that for any arbitrary vector u in w, its inverse, additive inverse, must be there as well, right? That must be true if w is a vector space. So let's let w be in w. So let little w, the vector, be in the vector, in the subspace w, or sorry, in the set w. Okay, so what do we know? Well, w is a subset of v, so that means w is in v. Okay. Now, previously we had a theorem that said, so from previous theorem, -1, the scalar, times w is the additive inverse of w in the vector space v. Okay. Now, since w is closed under scalar multiplication, again, that closure property that we've assumed, that tells us all we need to know. Since w is closed under scalar multiplication, what do we get? Well, -1 times the vector w must be in w, right? Which implies that the inverse, because this is equal to the inverse of w, right? That implies that the inverse of w is in w. Okay. So that's the demonstration of 4. So 3 and 4 both rely heavily on the fact that w is closed under scalar multiplication. So you can, if that's true, in order for that to be true, then the additive identity and the additive inverse must be in the subset also. Okay, and that's it. So 1 through 8 are true, plus closure, so we got it all. Okay. Perfect. So it's a little bit of a longer proof, but hopefully you can see that that is, that greatly simplifies our job of identifying whether something is a subspace or not. If you're given a subset of a vector space, is it a subspace? You've got 2 things to check. Is it closed under addition? Is it closed under scalar multiplication? If so, it is. Okay, let's do an example. Let's take a look at an example here. So consider the set UN of upper triangular n by n matrices. Okay, so UN is the set of upper triangular n by n matrices. Now clearly U of n is a subset of M n. So it's a subset of n by n matrices, right? Not every n by n matrix is upper triangular, but every upper triangular n by n matrix is an n by n matrix. Okay, so clearly un is not empty, right? We know that. I mean, anybody can imagine an upper triangular matrix, so it's obviously not an empty set. So in order to confirm that un is a subspace, we need to verify closure. So we can verify closure. Oh, so we can verify subspace by checking closure. Okay, simple enough. Okay, so we need to check that un is closed under addition. So let's let a and b be in un. Okay, and we'll write them out here. A, just so we can remember what this looks like. So a is a11 dot 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 a and n, and it's 0 below the diagonal and 0 or non-zero, whatever the case may be, above the diagonal. Same for b. We'll write b11, bnn, 0 below the diagonal, and whatever above the diagonal. Okay, so this is what these matrices look like. This is what the elements of un look like. Let's take vector addition first. Okay, so a plus b. Well, what's going to happen, we're going to have a11 plus b11, ann plus bnn, right? Everything below the diagonal, it's going to be 0 plus 0, right? 0 plus 0 across the board below the diagonal. Above the diagonal, it's going to be anything goes. A number times a non-zero number plus a zero number, a zero number plus a non-zero number, or 0 plus 0. It could be anything up above. We don't care. What's important is that everything below the diagonal is 0. And that's what you'd see here, right? Okay, so that's straightforward, right? So u of n appears to be closed under addition. And then what happens if I use scalar multiplication here? All right, if I take a, the scalar a times the matrix A, right? So that's a times a11, a and n, 0 star. Yep. So basically, everything below the diagonal is going to be 0 times a, which is going to remain 0. And so the diagonal will get scaled up by a or down, whatever the case may be. And then the off diagonal will, again, be kind of whatever. Right? And again, the important part here is to keep in mind that everything below the diagonal is 0. And that you can easily see that that's the case. Excellent. Okay. Great. Let's do another example. Right. And so what can we confirm? Right. I guess on the end of that. So un is closed under addition and scalar multiplication. So un is a subspace of m and n. So it's a subspace of n by n, of all n by n matrices. Okay. Another example. Let's do something maybe more concrete here. Let's let W be the set of vectors in R3 of the form A, B. So the first two components can be anything under the sun, but then the second component, or the third component, would be 1/2 A minus 2 times B. Okay, so basically the third component is half the first component minus twice the second component, right? So the first two components can be anything in the world, but then the third component is half the first minus twice the second. Okay, let's see if this is a subspace of R3. So so clearly this is a subset of R3, all right, and it's non-empty. I mean, I could easily think of any vector. I could just plug in a 1 for A and a 2 for B, and I've got a vector. So it's non-empty. So we need to check that it's closed. Okay, so how do we do that? Well, we just take two arbitrary elements in W, add them together, and see if it remains in W, the sum. So we'll let W1 and W2 be elements of W. Okay, and we'll just add them together. W1 plus W2, right? And let's write them out. So it'll be A, B, and then 1/2 A minus 2B. We'll call that W1. And then W2 we'll just say is C, D, 1/2 C minus 2D. Okay, now let's add this up and see if it maintains that same property. Okay, so what do we get here? A plus C is the first component. B plus D is the second component. And then the third component would be 1/2 A minus 2B plus 1/2 C minus 2D. Okay, so we've got that. Now this third component's where the question comes up, like how can we simplify this somewhat? And the answer is yes, of course, we can simplify it. Okay, so that's equal to A plus C, B plus D, and then 1/2 A minus 2B plus 1/2 C minus 2D. All right, so just getting rid of the parentheses and flipping a couple signs because we're subtracting. Okay, and then we can group this. We've got A plus C, B plus D, and then let's group the A and C together here, and we can factor out the 1/2, right? And then group the B and D together, and we can factor out a -2. And there we have it, right? Does that look right? This is in W, isn't it? Now notice here, that piece there is the first component. We're taking half the first component. And then this piece here is the second component, and we're subtracting off twice the second component, right? So when I add them together, the property holds, the relationship holds. Does it work for scalar multiplication? So if I take K times W, which we'll say is K times AB 1/2 A minus 2B, well, what do I get here? I get K times A, K times B, and then I get K times 1/2 A minus 2B, like so, right? And what I can do here is I can say I've got K times A, K times B, and then I can just like distribute the K into this, right? So it'll be 1/2 KA minus twice KB. Let me rewrite that. So KA, KB, 1/2 KA minus 2 KB. Okay. Right, and does that fit the form? It does. It's in W. Now notice here again, the first component, we're taking 1/2 of it. The second component, we're subtracting twice it. Right, so you've got that same form, right? That third component is dictated by the first two, which can be anything. And so you can see that. You can see that here. Perfect. Okay, Very good. Very good. Okay. This idea of a subspace is going to be very important for what is to follow, and kind of hinting in the direction in which we will be moving will be the next theorem, which talks about linear combinations and subspaces. So let's let W be a subspace of a vector space V. And let's let V1, V2, dot, 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 Vn be vectors in W. Okay. Then for any scalars, A1, A2, dot, 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 An in R, the linear combination A1 V1 plus dot 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 plus An Vn is itself an element of W. Okay. Now, this might seem obvious because what is this? This is just scalar multiplication and vector addition being performed on vectors in W. So doesn't the definition of a subspace get you this automatically? Well, what we didn't show in, what's maybe in question here is whether or not long strings of vector sums like this and scalar products can be attributed, will remain inside of the vector space. Okay, so I think to prove this, it's pretty easy, actually. It's almost too easy, especially if you just use induction. Okay, so we're going to using induction. Okay, let's let n equal 1. Then if V1 is in W and A1 is a real number, A1 times V1 is obviously in W by definition of the subspace. By definition of subspace. W is a subspace, so it's going to be closed under scalar multiplication. Okay. Okay, and so then, you could make this really obvious, the mechanism, by doing n equals 2. So let n equal 2. Then if V1 is in W, if V1, V2 are in W, and A1, A2 are real numbers, well then A1, V1 is in W for the reasons we just said. A2, V2 is in W for the reasons we just said. So these are two elements in W. When I add them together, you get something in W as well, because I'm starting with two vectors in W, A1, V1, and A2, V2. When I add them together, I stay inside of W because of the fact that W is a subspace. Okay. And so let's assume, we just showed it for n equals 2, but let's assume the statement is true for any linear combination. Any linear combination of n vectors, and consider n plus 1. Okay, so here again we'll let V1, V2, dot, 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 Vn, Vn plus 1, these are all vectors, be elements of W, and A1, A2, dot, 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 An plus 1 are real numbers. Okay, and so by our induction hypothesis, we know that the first n of them are, we get closure for the first n. So a1 v1 plus a2 v2 plus dot 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 plus an vn is in W. And we also know that an plus 1 vn plus 1 is in W. And so for the same reasons as before, we can just combine these two. This is a vector in W. This is another vector in W. I can add them together, and I get another vector in W. Right? So a1 v1 plus dot 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 plus an vn, right? Plus an plus 1 vn plus 1. That must be in W as well. Okay, and so that's the proof. Really straightforward. As I said, almost too simple, right? But you may have seen that theorem and immediately thought, oh yes, it's obviously true. It's just the two operations that you associate with vector spaces that's all that's being done here, and so it doesn't matter how many times I do it, right? But this just kind of makes the mechanism a little bit clearer. Okay, and so that gets us really close to the end. I want to do one more theorem, just because it's very closely aligned, and it also deals with something that we just talked about in the previous couple sections. And that's going to be Eigenspace. Right, so here's the theorem. It's a nice one, simple enough to prove as well. Let's let A be an n by n matrix. And let lambda be an eigenvalue of A. Okay, and we'll say having eigenspace, which we'll denote by E lambda. Okay, and so the theorem basically is that this eigenspace is a subspace of Rn. E lambda is a subspace of Rn. Okay, so that is the theorem. Now this is another really, on the surface you may look at this and think to yourself, man, this is not straightforward, because Lord, eigenspace, I got to think about eigenvectors now, and I got to think about, eigenvalues and everything else, and this proof might be really tricky, but all we need to know to prove it is that E lambda is a subset of Rn, and it's non-empty. And then once we have that, everything comes very quickly, right? So by definition, what is E lambda? Right, so if you can't remember, you could go look, but it's basically the set of all vectors such that A times that vector is equal to lambda times that vector. That's the definition of the eigenspace, right? Okay, and so keep in mind this includes the zero vector, right? Right. So now technically 0 is not an eigenvector. The zero vector is not an eigenvector, but it is part of the eigenspace, right? Because it fulfills this property. Okay. And so what can we say about E sub lambda? Well, E sub lambda is obviously non-empty, right? First of all, lambda as an eigenvalue exists, and so it must have eigenvectors. And second of all, we know that the zero vector is in there automatically, so it's non-empty. Okay, and so that means we just have to prove that it's closed under addition and multiplication in order to show that it's subspace. So let's let x1, x2 be two elements in the eigenspace, and we need to add them together and show that their sum is in the eigenspace. So to show that x1 plus x2 is in E lambda, we need only do what? Well, start with this. Okay. Right. Remember the definition of the eigenspace is that it's any vector that fits this form must be part of the eigenspace. Right. So let's start with this and see if we can get to this. Right. So A times the sum of x1 and x2. Well, we can distribute like so. Right. Since x1 is in the eigenspace and x2 is in the eigenspace, by assumption, that means ax1 is equal to lambda x1 and ax2 is equal to lambda x2. And then, of course, you can see that that gets us this. Right? And so this right here tells us that x1 plus x2 is in the eigenspace. Okay, so we know that's true. Now what about scalar multiplication? Okay, so for scalar multiplication we can do the same thing. Let's let c be a real number. Okay. Then what can we do? Well, a times cx. Right, what we want to show is that the same relationship that we saw here holds when we take the vector times this constant, or this scalar c. So we know that we can change the order here, right? Namely, we can multiply c by a to start with, right? So we can write it, like this instead, right? And that, of course, means that this is equal to c times lambda x, which, now you've just got two constants here, two scalars, and so the lambda can be brought out front, the c can be put back in, and you get to this, right? So here again, a times some vector equals lambda times some vector. So c times x is in e lambda. Okay, and what does that mean? Well, we have closure. E lambda is closed. And that implies E lambda is a subspace of the vector space Rn. Okay, perfect. Perfect. So very simple kind of proof, just uses a straightforward definition of these things and does a good job of kind of making clear what's going on and how the subspace works. All right, so I think that's where we'll end it. Very good. And now next time we'll get into a very interesting topic, and that is the topic of, it's called span. And so we'll talk about what it means for a collection of vectors to span a space. Okay, so until then, take care, and we will talk to you all later.